Hello, everybody. Good morning. In the name of Allah. Hopefully, we are having a hybrid meeting, hybrid class for those of you who are online. They should be active in the class, even if they have any questions. Start your microphone. It doesn't require to raise your hand, so maybe I don't see it. Just start your microphone and talk so I could understand what are you saying. And in the class also, if you have any questions, raise your hand. Okay, if you remember, we were almost finished for our first version of datapaths and control. It was a single cycle MIPS, a processor, single cycle. Everything would be done in just one clock cycle, and at the end of each clock cycle, the next PC would come, and the rest of the data paths working on the new instruction. So in every clock cycle, we have a register. We call it PC register, and the PC comes to data path, the new PC. Then everything is working. Instruction is coming from the instruction memory. Then it is going to be decoded, and we find out which opcode it is, which registers do we need, if there is any intermediate value, immediate value. Then we go to ALU. It goes by itself with a combinational circuit, and everything would be it would work for the thing that, or the instruction that it came from the instruction memory. So that's what we have discussed before, and there were three main type of instructions. R type. In R type, we have opcode and function. These two together make ALU control, so we know what ALU should do. These two together make all of the control signals, which control signal should be active, which one should not be active, which one should be 0, which one should be 1. And then we have three registers, RS, RT, and RD in our format. Then we had load and store. There are different instructions, but they follow the same format. In load or store, we have opcode, which is 35 or 43. I don't remember, 35 was for load or for a store. One of them is for load, the other is for a store, 35 or 43. Then we have source register, which is the base address of the memory that we are going to work with. Either it is in load, then we read it from that position. If it is a store, then we write in that address. Then we have the next register. For load, this register is the destination. When we get the data from the memory, then we put it in this register. For a store, this register is the actually source, is actually the thing that we get it from the register file and then store it in the memory. Okay? Any questions, any comments? Everything clear? And then we had branch instructions. So they follow immediate format, I format. Also load, store, follow I format. In branch, again, we have the opcode, which branch unequal. We just talked about branch unequal. In the real MIPS, there is branch unequal and branch not equal. But here we are just talking about branch unequal. The opcode is 4, and it has two registers which are compared together. Branch unequal, RS, RT. They are compared, and if they were equal, then the target address would be calculated by this immediate value, which will be added to PC. So we get the new target address. Okay. So we talked about this, and then we have seen the whole data path. Then it's good to see how each instruction changes, not changes, works with different parts of data path. Based on the instruction, different parts of data path are active. So we will see that in the next slide. And we talked about control signals, which are regdes, regwrite, ALU source, PC source, memread, memwrite, and mem2reg. And we talked about these control signals in our data path, which is here. You see these control signals, they are all here. They are just determined, calculated based on the instruction. We get the instruction. When we fetch it, we get the instruction. Then we decode it. In the decode section, the control signals will be generated, and they are going to different parts of the data path. As you could see, there are different controls anywhere in the data path that we will see. So these were control signals, and you see for R format ALU operation, how would be the control signals. For a load signals, how are they? For a source instruction, how are they? And for a branch and equal, you could see this. Yes, please.
So whenever the signals are zero, does that mean they're not in use, or?
No, some of them, they are just selecting. For example, let's go back here. For example, let's say that this signal is zero. Let me erase everything here. The question is, when it is zero, does it mean that it is not active? I am saying that no. For example, look at here, ALU source. If this is zero, it means that ALU source coming from here, so it has a meaning. It doesn't mean that it is not active. And if it is 1, then it means that ALU source coming from the immediate value. So it has a meaning. But some of them, yes, they mean that if they are asserted or not asserted. For example, let me bring this table. Here is the table. You see, there are 2 columns. Effect when deasserted, effect when asserted. For example, these 2, memread and memwrite, they are the control signals, which when they are not asserted, actually they are active high. So when they are 0, as you told, they don't do anything. It just means they are inactive. But the other things, or for example, this one, regwrite. Regwrite also, when it is 0, it means that it doesn't do anything. But the other things you see, when it is 0, it means something. When it is 1, it means something else. Very good question. So this, okay, now look at the R-type format. How could I make it better so you could see the whole page? I guess, how could I get rid of this? Could I? There should be some kind of minimizing. I don't know. How could I? Okay, I put it. Maybe I cannot do it. Okay, I leave it here. So the slide is R-type. So if we are R-type, then it means, for example, we have an instruction like add. So let's go through each element one by one. From PC, we get the instruction. So instruction is coming here, 32 bits instruction. The opcode is 0. The function code is something which shows us this instruction is add. Then we have 3 registers, RS, RT, and RD. RS and RT, they go for read registers. Read register 1, read register 2. You see, we are now looking at R format. When we have R format, this is what happens. So everything is here. And you see, when it is R format, it means that this line is not isn't active, because in R format, RT goes for the read data too, not for the write data. RT is for write in load instruction, not in, for example, add instruction. Do you follow? If you have questions, please ask. So, and here, this third register coming here, and it should go to write register. So what is this multiplexer at this time? This multiplexer, as you could see, this path is active. The selected path is this, not the other one at the top, which is grayed. I showed you it has been grayed. It's grayed. So this is active. So the third register coming to write register. So this is the register. Let's move on. And also you could see here that we don't have any immediate value here, so the sign extend shouldn't work, or if it works, it doesn't have to do anything, because everything which will be calculated, you could see it is not selected with the multiplexers. So this also is inactive. And what else could we see here? Then let's move on. So the calculation, the ALU results, the read register 1, which was RS coming here, the RT coming here. Again, this multiplexer, this pass is active, not the pass from the immediate value, because it is RT. So RS, RT coming to ALU, the result is calculated. And you see, when the result is calculated, it doesn't go to memory. We don't, it is not, for example, a store or load that we would like to calculate the address. So that is grayed out. But this result, ALU result, coming here to this multiplexer, and this multiplexer, this pass is deselected, is grayed, and this pass is active based on the control signal here. So this is working, and the ALU results coming back to write data. And the red write, where is red write here? Red write, it is red write. And the red write is active for this instruction. Red write is active, write data has come. So the ALU result will be written on RD, the register RD. Okay? So you see, in R format instruction, the multiplexers select what should go to where, and what is active, what is, it is not active, it doesn't do anything. So this is the whole, you see, for example, here, we don't have anything to do with memory. It is R format, RS, RT, RD. We don't have anything with memory. For example, we don't have anything with the sign extend, because we are not using the immediate value in our format instruction. And we don't have anything to do with the PC. We don't calculate the target address, because it is not a branch. So these things are working in our format. Okay. Now let's go to the next instruction, load instruction. Sorry, the top has gone, so we don't see it. I guess online students, they see it, that top, but here we don't see. I could bring this down to see that it is a load instruction, and I put it back again. So load instruction. Load instruction. Instruction is coming here again. The same thing that we are starting every time from here. The instruction is fetched. When the instruction is fetched, the first 6 bits is opcode, and I guess it was either 35 or something, I don't remember. So it is load. So it is load. And the control signals are determined based on a load instruction, which we will see what they do. And the instruction is coming here. So this is the load instruction. In load instruction, we have RS, RT, and an immediate value. The immediate value is the offset of the address. The RS is the source of the address, the base of the address, and RT is the destination that we will write on that register. Okay? So as you could see, RS coming here, always RS is here. There is no selection, no multiplexers in the path of the first, in the RS. But RT doesn't come here. We don't need to read RT. There is only one read, which is RS, which will be space address, and then it will be added to the offset. So you see, this is inactive. Grayed out. This pass is grayed. We don't have read register. But for this RT, this time this RT acts as the write register. We are going to write on this register, RT. So here you see this multiplexer is 0. The control of this multiplexer now is 0, which means that the value, the RT value, goes to write register. And you see here, this multiplexer, the second pass, this pass is gray. We don't get RT from bits 15 to 10, which we did it to the previous, for the previous instruction. Here, we don't have anything meaningful for instructions 15 to 11. So we just get it from here. Okay. So now we have this register is going to be read, and the register is coming here, which would be the base address, base. And the immediate value is the 16-bit of instruction. The instruction is here. The 16-bit, the 16 lower bits of instructions coming here, they will be sign extended, because it could be either negative or positive value, the immediate, and it is sign extended, and this goes to ALU, the other operand of ALU. You see, the multiplexer here selects this one, not the one coming from the register file. Yes.
So instructions 20 to 16 are going, or is giving the multiplexer 0, right?
Yes, the multiplexer is 0 here, so it means that this is selected,
So
not this one.
So that'll make that source register RD, or like the destination register.
RT would be considered as the write register here.
Okay.
Yeah, because we have load. Load means get something from the memory and then write it in the register. For example, load T0, offset with RS. RS is the base address here. So RS is coming here, and immediate value is coming here. They are added together. So now we have the address. Base plus offset is the address. Address goes to data memory. In memory, what do we want to do? We want to read from memory. So if you look at here, the memory should be active now for load instruction, and memwrite would not be active. I wish we have created this out so you know that memwrite is not active now because it is a load, but memread is active. Memread is active. Address is here, so memory reads, memory find the content and puts the content here. The read data coming here. So now we have read from the memory. This should go and be written on the register. As you could see, the select of this multiplexer for the register target is selected the first pass, not the second pass. This is active, not this one. This one was active in the previous instruction. So the value from the memory coming here, going to the write data. So write data is coming here, write address, write register has come from RT, and it is written on RT. This is, and you see also here in this instruction, we don't have anything to do with calculating the address, so this is not active also. Okay? So this was the load instruction. So any questions from online people? Omar, Hassan, Dangshi, I don't see you. Turn on your webcams. Okay, next instruction. Next instruction is what? Is branch unequal instruction. This instruction, branch unequal, again, it follows the R format. So PC coming here, we have PC, the instruction coming out here from the instruction memory. It has 32 bits. The first 6 bits is the opcode of BEQ. It was 4, I showed you before, something. It is the opcode of branch unequal. Based on the opcode, the control signals will be calculated and the signals will be generated. We will see how they are generated. In branch unequal, we have RS, RT, which will be compared together, and then we have immediate value, which is the displacement to the PC. It should be added to the PC after it has been multiplied by 4. So let's see. So the first 5 bits shows RS, which again, it comes forward to register 5. The second one is RT here. RT acts as the read register 2 because we are going to compare these two registers together. So these two registers going to ALU. Again, you see this pass is active. The next operand, the second operand of ALU is read register, read data 2, which is RT. RS and RT are here now. RS is here. RT is here. And what does ALU do for a branch unequal instruction? What does it do? The operation of ALU? We want to compare them. So what do we do? Subtract. So ALU control, ALU, where is ALU up? Where is here? So ALU control force ALU to do subtraction. And when calculating, when subtracting, the result doesn't go anywhere. We are not going to put the result of the subtraction anywhere. We just needed to see if they are equal or not. So we just need this 0. If they are equal, then the subtraction result will be 0, and this becomes 1. This 0 becomes 1. This becomes 1. So where were we? So we talked about RS, RT, comparing. And now here, in this part, immediate value will be sign extended, because the displacement also could be positive or negative. It could go back to a place up, for example, in a loop, or it could go down to the code. So it is either a positive value or a negative value. And this sign extended value coming here, shift left 2 means multiplied by 4. And this will be added to the PC. And the result is the new is the target address, the new PC, which will be selected based on the result of the branch result, branch outcome. So let's see. If the branch outcome is 1, it means that they were equal. And the instruction were branch, which it is branch. We are not talking about the branch. Both of them would be 1, and this AND would become 1. This AND would become 1. When this is 1, it means that the multiplexer selects this pass, not the pass at the top. This is when it is 0. So this is selected, and this is the target address. The target address is coming here, going to be ready for become the next PC. This target address is PC plus 4 plus displacement. It has become ready here at this position, and then this multiplexer transfer this for the next PC. So if the branch, the Z was 1, it means they were equal. Let's say if they are not equal. So if they are not equal, so let's see what happens. So if they are not equal, then the 0 calculated by ALU, when it does subtraction, the 0 will become 0. It is not, they were not equal. So 0 comes here. Even if the instruction is branch, which is branch, it is 1 here, but 1 and 0 becomes 0. So we have 0 as the selector for the multiplexer. So this will select the 0 input, which is PC plus 4. So PC plus 4 is selected and goes here, will be ready for the next PC. It means that branch was not taken, and the next PC would be the regular PC, the PC plus 4, which will be fetched from that position. Okay, so this was the next instruction. So you now should have a very good understanding of how the single cycle processor works. Data pass, control pass. How data pass acts and how control tries to put the required pass and the required components for each instruction. Okay? So I guess here is the last one for the data pass and control pass. And then we will go for our lab 4 for those who are selecting the new lab 4, and then you can implement that later in the file. But there is one instruction left, which is jump. So this is implementing jump. We haven't talked about jump yet. We had our format, add, sub, like that. We had load, we had store, we had branch and equal. We didn't talk about jump, which was inside our limited set. At the beginning, I told you that we are going to implement these 5 instructions. R format, arithmetic and logic selected, arithmetic and logic and, or, sub, and that's it, I guess. I don't remember exactly. What was that? And then we talked about load, store, branch and equal, and jump. Let's see jump. Let's go to jump. Jump is a 32-bit instruction like anything else. It has an opcode, 6 bits opcode, which opcode is 2. So the 6 bits is 2. So it is, if you look at jump, then it is 0, 0, 0, 0, 1, 0. It is 2, 6 bits of opcode for jump. And then we have 26 bits of address. This is the target address. And we talked before that this is 26 bits, but the target would be, how many bits do we need for the target? Yeah? 32, yeah, you are not here. Online student, if you know the answer, please start your microphone and tell me. 32 bits, that each address in the instruction memory has 32 bits. We have 26 bits here. We multiply it by 4, so there is 2 0 coming here from multiplication by 4. And then 4 bits, the most significant 4 bits coming from the PC. So 4 bits from PC, 26 bits from the instruction, and 2 zeros added there. Here you see jump uses forward address, update PC with this address. Jump goes there. It is not a branch. It doesn't depend on a condition to be taken or not. It is jump, so it goes there. And the top 4 bits of the PC plus 26 bits of the address from the instruction and 2 zeros, which is the multiplication of 4, and it will form the 32-bit address, and then we go for that. So to calculate this, to select this address, we need another control signal, which I haven't showed you before, but here you see. This is the next control signal as jump, and this is going to select here the next target PC. Before that, this multiplexer was selecting either PC plus 4 or the target address from the branch. Before that, we talked about it. And it was here. And in the previous slide, the output of this multiplexer went here. But it was not complete. It was not completely correct. So now I am showing you the complete design. So the thing that we had calculated before is another input from this, this is another input from this multiplexer. And the other input of this multiplexer is the jump address. What is jump address? Jump address, the 26 bits coming from the instruction, and the 4 bits of PC coming here, which will form the most significant 4 bits, and these 26 bits multiplied by 4 actually shift left 2, so we have 28 bits coming here, 4 bits coming here, the 32 bits is formed coming here. If it is a jump instruction, jump is 1. This control signal is 1. And this 1 coming here, and it means that in this multiplexer, the one input, which is the jump address, is selected, and the output of this multiplexer goes to PC. The next PC would be the jump address. Okay, so this is, and you see in the jump instruction, we don't have anything to do with the register file. We don't have anything to do with the ALU. We don't have anything to do with the data memory. Just instruction comes, jump address calculated, not calculated, just concatenated. 4 bits from PC, 2 zeros, they are concatenated, and the address will be calculated. You see, data path is very simple. Okay, so this was the last instruction that we have talked about. Okay, any questions? We finished. The single cycle CPU or processor implementation is finished. And you now have a very good view of the processor. There are things that we could discuss now and leave the rest for the next course, the next advanced course. As you could see here, there are different instructions. Add or format, load, going through the store, branch, jump. There were different instructions. And as I showed you, they uses different parts of the data paths. For example, it seems that jump is very small. It's using just this concatenation. And it seems that jump would be very fast. The jump address would be available very fast. So this is fast. But for example, let's see another instruction. This is, what was that? Let's go to branch. For example, this is branch. Branch, again, we have ALU in the past. We have register file in the past. So they are taking times. Each one of them is taking times. And then the result goes to multiplexer. So we have almost 2 components in our pass. The multiplexer has a very small delay, so I don't look at them. The sign extent is just repeating the last bit, so it doesn't take time. But register file, ALU, they do something, so they take time. So I look at them. So it is 2 components. But let's go to, for example, R-type instruction. R-type instruction, register file is inactive, so it takes time until the register is coming out. Then we have calculation on ALU. So again, we have something in ALU. It is like a branch. And then we don't have memory, and that's it. So it has 2 elements working and making the delay until the next PC would become available and everything has been settled, done. If we want to write on register, we have written. If we want to write on data memory, we have, and so everything would be done. Now let's look at load instruction. Load instruction, register file is active, ALU is active, data memory is active. So it seems that it has many things to do in load instruction. And I can guess that this instruction would be the longest. It has the longest delay and compared to the other instruction. I wish we had a store also. For a store also, we have this, we have this, we have this also, and then writing to the register file. But a store is also using all of the things, but there is a difference between a store and load, which I think, again, makes load longer than a store. Because in a store, we read from memory and write in register file. But in load, we write in memory. Writing in memory takes more time than reading from memory. So I guess actually we have to do the simulation and calculate what's the delay. But my guess would be that the load would be the longest delay. Would be similar to a store, then R format instructions, then branch instruction, and maybe the shortest was the jump instruction. So you see, these instructions take different, they have different lengths, so they have different delays. When we have different instructions taking different delays, then, and we want to, everything would be done in one clock cycle. How do we select our clock cycle? How do we? Of course, we should consider the longest one, because if, let's say, do I have any number? No, I don't. Let's say a jump takes 200 picosecond, branch takes 400 picosecond, and this is 4, not 9. And load, for example, takes 800 picosecond. So if you pick 200 picoseconds for your clock, then it means that the load instructions doesn't work. Load is in working, the things are working in the load instruction, then the next clock comes. So it is not complete, so it's not good. Therefore, we have to select the clock cycle as our longest delay, which, as my guess, is the load. Load, we have to look at the load and pick up that. So, critical path is load instruction. Critical path here is the load instruction. We should calculate. Actually, we should calculate the delays of all of the instructions and see which one is the longest. You see it in the load, we have instruction memory, instruction comings out of the fetch. Then we have going to register file to find the RS and RT in load. Then we go to ALU to calculate the address based on the base address and offset. Then we go to data memory and load something from the memory. And then we have value and we have to write it in register file. You see how many things that we are doing in the load. So it's taking a lot of time. In a store, we don't have the last part. We just put something in the memory, but that's it. That's it. So I guess a store is shorter, load is longer. And we cannot have different variable clock cycle. For example, we see if the instruction is branch, we go to 200 picosecond, 400 picoseconds. If it is jump, we go to 200. It's not possible. There is one clock that we are generating, and it goes to everywhere in the datapaths, in the processor. So it is not possible that we have variable clock cycles. It is one clock cycle. So we have to select this. And if it should be varied, it would be, it's not possible. I guess it's not possible, and we cannot work it out. And this kind of implementation, which forced us to use the longest path for our clock, is some kind of violating our common case fast. We are making everything slow because of the longest delay. We are not making the common cases fast. So whatever it is, it takes, for example, 800 picoseconds. That's it. We cannot do anything about it. So what to do? What to do? The solution is pipelining. So the solution is pipelining. Oh, I will introduce the concept of pipeline for you. we had some groups that they are doing pipeline in their projects, so they get the idea. I'm sure that they have the idea up to now because they have already started their projects. But I will give you the idea of pipeline. But in our course, we don't go to implement the pipelining in our processor. So let's see the pipelining concept. Pipelining analogy. We use washing cycle, laundry as an analogy for pipelining. I guess I've told you before in one of the sessions about the pipelining and the pipe and the laundry. You see how parallelism in using a laundry room will improve the performance. Let's say that we have a laundry room, that it has a washer, a dryer, a folder, and a storage for putting the clothes there. So we have 4 things to do in the laundry room. When you go to the laundry room, you put your clothes in the washer, then it washes. After it finishes, you get it and put it in the dryer. Dryer dries it, and then you go to the folder, you put the clothes, you fold them, you make them good, and then you store them in somewhere to go, so whatever it is. So this is the thing that we will do in laundry room. The first implementation of the laundry room is that there are 4 sections in the laundry room, but whenever somebody goes there, it locks the door. So I go there, I lock the door, so I will be there until I finish. When I finish, I go out and the next person comes in. This is one kind of using the laundry room. So I go there, I go there at 6 p.m. I put washer, everything, let's say everything takes 30 minutes, half an hour. So I put my clothes here at 6:30, I take them out, put them in dryer. At 7 p.m. I put it in, I fold them, and then at 7:30 I store them in the place. It takes 2 hours for me to do that. And then I go out at this time, and the next person comes in. Again, this person using the machine, 8 p.m. starts, and 10 p.m. finish. The next person comes at 10 p.m., and it is finished by 12 a.m. And the next person starts in the midnight and done by 2 a.m. Okay? So if you look at this, it is 8 hours for 4 loads. So every load took 2 hours. It's obvious. Every load takes 2 hours. Okay. But we could do something else. If I go there and use the washroom at 6 p.m., I start at 6 p.m. and finish, the washroom is finished by 6:30. I took my clothes out of washer and put them on dryer at 6:30. Now the washer is free. I am not using the washer. So the next person could come at 6:30 and use the washer. Okay? Yeah, it's obvious, it's clear. I guess everybody does this when goes to laundry. And the second person, B, person B, uses washer at 6:30. At 7 p.m., I am done with dryer, so I took my clothes off and put them on folder and start folding, and now the dryer is free. So person B used the dryer and puts the clothes, his or her clothes in dryer. And now the washer is also free. So C is coming in, and C at 7 p.m. starts washing. Okay? Again, at 7:30, I go to storage. B goes to folder, C goes to dryer, and D can come in and use the washer. So D starts working here. Now at 8, I am done. I go to my room. At 8:30, B is done. C is done by 9, and D is 9 by 9:30. So how many hours it took? 6 from 6 to 9:30. So 30 and half hour it took. For how many loads? For 4 loads. We had 4 loads. 4 loads. So each load is taking how much? 3 times 60 is 120, 210 minutes divided by 4. It is about 52 minutes compared to 120 minutes for this, 2 hours for that. So using some kind of parallelism, we could achieve speed up. We could achieve better performance. Here, let's say our speed up is how much? Our speed up is 120 minutes to 52 minutes. It's about 120 to 52. How much is that? 4, something like 4. So we have achieved at 4 speed up, which is very good. I guess I have done something wrong. No? That's good. 3, 4. Yeah, it seems right. Yeah, so that's a good speed up. I don't believe it's something, I guess it's right. Anyhow, if you look at this, there's something that you should notice here. When I go to the room and then I exit from the room, still at 8 p.m. I go out. So the latency for me to finish my job hasn't changed. It's still 2 hours. I have to be there for 2 hours. My latency to do my machine hasn't changed. But it's not important. The important is throughput. How many works do we do in a specified time? This is important. And this is how pipeline helped us. The latency, we don't care about the latency. In the processor, we have billions of instructions coming to the processor. So if the latency of each instruction is still the same, let's say 800 picosecond, as we talked about it in our single cycle processor. Who cares? We care for throughput. How many instructions is done during a specified time? This is important. So pipeline doesn't help latency. It just improves the throughput. And this is important for CPU, for execution time, for instructions for the program to be done. The next thing that we could notice here, that if I had more people coming after 2 a.m. also, so always we use the machines, it was better because you see, during this time, actually this time, at the 3 first slots, we are not using the full capacity of the room. We are using at one time only 1 machine, at the next time 2 machines, the next time 3 machines, and then we go to the full force of 4 machines later. And again, at the end, we drain out. So here we have 4 machines. Again, here it is 3 machines, 2 machines, and 1 machine, which is not good. So what would be good? If we keep the pipe full every time. So everybody comes after D, E comes, F, G, H. If we do that, then we have something at the beginning, we have something at the end, which is not important because we have billions of loads using 4 machines, and that would be almost a speed of the maximum speed up because all of the machines are working together. But at the beginning and at the end, okay, we don't use the full machine, which is not important because if you calculate billions times, it's just one machine. But there are 1 or 2, 3 at the beginning and something at the end. It is nothing compared to billions. So these are things that we could notice from this simple example of laundry. So we had 4 loads. It took 8 hours. Okay, I told you something is wrong. The speed up is 2.3. I don't know how did I calculate 4. 2.3 is the speed up. It is not 4. It is 4 when we have lots of loads coming together. If we have only 4 loads, then it becomes 2.3, which is good, actually, which is better than 8. It's better than 8 hours, but the speed up is 2.3 because of this section. The only section which we have 4 machines working together is at this time. If we have non-stop, we have n loads, which n is a very large number, let's say billion. If we have n loads, then the times for doing sequential is 2 times n. 2 times n is the sequential one. Each load takes 2 hours. But the times for those loads which are working together is half an hour, so half an hour, but we have something at the beginning, at the end, which I added 1.5 here. So if you calculate that and n is very big, then 1.5 would be discarded. So I guess I have written it back. It is this, 2n divided by plus 1.5. If n is very big, then this is discarded. You calculate it. You put n equal to 1,000. You see it is close to 4. You put it 1 million, it is 3.9999, and so on. Let's do it. Why not do it? So let me calculate. So let's say n is 1 million. So at the top, we have 2 million. At the bottom, we have 0.5 times million is 500,000 plus. So we have 2 million. 2 million divided by, where is divided? Okay, let me use this. Divided by 500,000 plus 1.5. 500,000 plus 1.5. This is the value. So how much would it be? 3.99999. You see, it is close to 4. So you can disregard 1.5. When is very, very large. When it's very large. So these are lessons that we learn from our laundry example. So what does it do? What does it have to do with the MIPS? Yes.
Sorry, just for the analogy, where's the 1.5 coming from? Like, what is that representing?
Okay, I guess it is here. It is 1.5 hours takes for the next or the first one and the last one to drain out. 1.5 hours. Um, so MIPS, okay, we have talked about laundry. What does it have to do with MIPS? In MIPS, we have instructions, we have program, and program has lots of instructions. And we talked that each instruction in a single cycle implementation takes different cycles, but we have to select the longest path for the instruction, and which was for the load instruction. Now, we are saying that if you look at the MIPS, and the MIPS is very regular, as we talked about it before. If you look at the MIPS, you could detect different jobs doing during the execution of an instruction. The first one is fetch. Fetch is always fetch. You have address, PC, getting something from the instruction memory. So fetch is the first part. Then instruction coming out, you have register file, you have decode, you have decoding instruction to generate control signals, and you have the register files to generate the registers. This was the second stage. We could distinguish it with fetch. Fetch, decode and registers, decode and loading registers. This is the second part. Then we had ALU calculations, executions of the add, and, or these things that we have used ALU for that. So this was the third stage. The fourth stage was using memory. In load and store instructions, we were using memory. So this is another things that we could distinguish among the works that we are doing. And the last part was writing the register back, writing in the register file. So we have distinguished, we have detected 5 different stages for the instructions. I am not saying that every instruction has all the 5 stages, but they do have these stages. Some of them have, for example, fetch and decode and ALU. That's it. Some of them has all of them, like load. Load has all of these things. So the first stage is fetch. The second one is instruction. IF means instruction fetch. The second one is ID, instruction decode, and register load, register feed. The third stage is execution. It goes to ALU to calculate whatever it is required. The fourth stage is memory. So it is either in load or store. We have this stage. In other instructions, we don't have this stage. And the last one is write back, writing to the register file, the value which is calculated. The value is calculated either from ALU or coming from the load from data memory. So they are going to be written back to the registers. So these 5 stages. Now, look at laundry, and then look at here. In laundry, we have 4 jobs that could be done separately. Go to washer, dryer, folder, storer. Here, we have different jobs. The first instruction comes and fetched. Then this instruction goes for decoding, and the next instruction goes for fetch, for being fetched. And the first instruction is being decoded. When it is done decoded, then it can go to execution, the first instruction. The second one can go to decoding. The next one can come to the fetch. And then again, so on. I again repeat, some instructions don't have all of the stage, but okay, they go one by one and they go to the stages if it is necessary. For example, R format instruction doesn't use the mem stage. It uses fetch, decode, execute, and then write back. Because our format instructions, they are calculating something based on the registers and then putting it back to the register. For example, branch instruction. Branch instruction is using fetch, is using decode, because it has to get the registers. It calculates the target address, and that's it. It doesn't have the memory and write back. Branch. For example, load instruction. Load has fetch, has decode, has execute, because calculate the address, going to memory to read, and then writing back the register. So load has everything. A store has fetch, a store has decode, a store has execute to find the address, a store has putting that value into the memory, but it doesn't have the write back. There is no writing on registers. So a store has these 4 stages. But we could detect these 5 stages and we could make it pipeline. If we make it pipeline, then in every clock cycle, one instruction comes to pipe and it starts from the fetch, then goes to decode, then goes to execute, then goes to memory, then goes to write back, and the next instructions coming inside. If we have done this, it means that now our clock cycle will be determined by the longest delay of these stages. We have to look at these stages carefully. What do we do in fetch? Fetch is just going to instruction memory and taking something out. Okay, that's it. What do we do in decode? Decode, we just get something from 6 bits from up and 6 bits from down and calculate something based on these bits for the control signals, and we get registers from different parts and going to register file. It is fast, I guess. It is fast. Execute, what does it do? It has 2 operands coming to ALU. We are calculating add, and, or. These things are also simple. It doesn't take time. We have memory. Memory, I guess, it's the longest one because it's memory. So we have to load and write in the memory. Maybe it's longer. My guess is that this is very time-consuming compared to other. And write back is also very simple. It's just putting one value into the register file. So let's say this is. So in load, we have, okay, here I've assumed that fetch and memory takes 200 picoseconds. ALU also 200, which I don't think it is, but okay, 200. But register read and register write 100 picoseconds. So for load, we go for 200, 100, 200, 200, 100. The total would be 800 picoseconds. For store, it is 700 picoseconds. For R format, 600. For branch, 500. For jump, it is less than that. And because of these things, we've thought about pipelining. Now, if I make pipeline, what would be my clock cycle? Look at the longest time for each stage. How much is that?
800 picoseconds.
How many? How much?
800?
No, 800 is the total for a single cycle. But each stage is these are the 5 stages that we have. How many?
200.
200, yeah, because we have either 100 or 200. The maximum is 200. So we can pick up a clock of 200 now, which is much better than 800 that we had for single cycle, yes.
So you said that certain instructions don't go through every single stage of the pipeline. So what happens if, like, say, an R format instruction is stuck behind like a load instruction, and then it reaches the stage where, like, for
Yes.
the load
The question is perfect. So for example, here in R format, we have this, and this, but we didn't have this. So what happens there? Our design principle was regularity. We have to make them regular so the design would be simple. If this is the case, we just make them regular. Even for the R format, we pass the instructions through 5 stages, but in the 4th stage, nothing is done for that instruction. Based on the control signals that you build, building control signals is not hard. You are very familiar with that right now. So using these control signals, we pass. So it seems that, for example, somebody comes there and say, I don't want to use the folder. I just want to use washer, dryer, and storer. We tell that person, you have to wait because somebody at that time is at the storer. You cannot go to a storer at that time. You see? Because somebody is there. The previous person is doing a storer job. So even if you don't want to use folder, you have to wait until the storer becomes available. Exactly here. We have 5 stages. Even the R format here says, okay, I don't need this memory access. We say, okay, wait until the next cycle comes and then do your write back. Again, in branch and equal also, we can do the same, something like that, the same. So the pipe is always taking all of the stages. But again, I repeat, the throughput is based on 200 picosecond. Every 200 picosecond, one instruction comes to the pipe. So that's important. So it seems that we have built a machine which works, which executes in each instruction in 200 picosecond. Again, I say, you know, it is not true. Every instruction, the latency of each instruction is something like 800 or 700 or 600 or 500 picosecond. This is the latency, but it has to go through all the stages. In the pipe, the latency is always 5 by 200, 1000 picosecond, 1 nanosecond. It is always 1 nanosecond, the latency, but that's it. This is the latency. The throughput is based on 200 picosecond. Okay? Yeah. So this is the single cycle, but for our pipeline, we use 200 picosecond. Here you see the pipe. So even if the load is everything. So 200 for this, 100 for register read, 200 for ALU, 200 for memory, and 100 for reg. Again, it has to wait all of the 1000 picosecond. It has only the load. I wish that we had other instructions. So even for, let's say, R format instruction and add, again, it comes to instruction, it's fetched. So the next, let's say the next instruction is add. So add is fetched here, then it goes for the execution, for decoding here, then ALU here, then nothing here, then write back here. So again, add is also taking 5 clock cycles, but it comes inside. Okay, so this is the single cycle. This is the pipeline, 200. If all stages were balanced, which was not for our case. In our case, we had 100 picosecond and 200 picoseconds. They were not balanced, so we had to select the longest one. If they were balanced, that was much better. So everything was based on that. So then you could use this formula, time of between instructions and number of states. But since it is not, so speed up is less and it's throughput. You can calculate that. I guess you can stop here And the design of a pipeline processor is out of the scope of our course, which will be in the next advanced course, we will talk about the pipeline. However, some of you have a pipeline as the project, so it is good that you will do that. So now everybody please make the quiz, which is the attendance. Online people also, and also in-person people. So the quiz, attendance, where is it? Attendance, July 7th, where is that? Selection, attendance, July 7th, okay. So please, it is 9:50. I will make it available for 9:50. What happened? 9:55. Okay. And the password is hybrid. And just give me a moment to make it available for you. Now refresh your writer space. It should be attendance for July 7. July 7 hybrid. The name is July 7 hybrid. And there is 2 questions that you need to answer. The password is hybrid, all small letters. HYBRID. Okay, thank you very much. Thank you for the online people. Tony, webcam is not available. Tony, what happened? Zimo, Azhar, Ishan, Anwi, Avnish, Hassan, Kevin, Anas, where is your webcam? So if your webcam is not on, don't put that my webcam was on at all times in the attendance part. So how was the experience? One of you, Avnish, how was that?
I really liked it.
What?
I really liked it.
Liked it? Said liked it? Okay. So it doesn't mean that we have to do it all the times, but
Yeah, I appreciated how.
okay, but we will do it. Yeah, okay, we will do it, but not all the times. It's good to have in-person class also. Yeah.
If it can be done on Fridays, that would be
Fridays. Yeah. Why not? Maybe one Friday we do it completely online. I will convince the next class, so I will stay home, doesn't come to school. So both of them will be online. And yeah, if I couldn't convince, then we have hybrid for your class. Yes?
Are we going to have class tomorrow?
Yes, at the beginning I told you, we have makeup class, but it is asynchronous. It means that I record the class for you, so you just watch it. But please, you do it either on Sunday or Saturday. Don't leave it for Monday, because you have to also reflect and do something for that. And that recording is the implementation of the datapaths that we have talked. And I am going to use Verilog also, so you would get something in Verilog, and you would have all the codes for the CPU, for the processor, and it is good for your Lab 4 also. So those who are going to use the new Lab 4, which will start from Monday, you could use the lecture to do that, yes.
So for Monday, we'll have 2 reflections to do?
Yes, I guess for the asynchronous part, I will make it later. For Monday, we have reflection for this lecture.
There's no quiz for the next lecture?
Why not? On Monday?
Not for Monday. You said upload one on the weekend.
Now, Monday, we have a quiz from the lecture of today.
Okay, but
Today, we didn't have.
none
So
weekend lecture. correct?
What?
None for the weekend lecture?
No quiz. You just have a lab for those of you who have lab, and also we have experiment. Yes?
I think you mentioned last week that you were gonna upload more like supplementary code for the lab. Are you
Yes.
going to be doing that?
Yes, in the lecture, I also, in addition to uploading the code, I am going to explain it for you so you have it under. It is part of the course, but it is good for your lab also.
And then will there be a DGD tomorrow or no DGD?
DGD, I am not sure. No? PA didn't tell you anything?
She doesn't say anything.
Okay, I don't know. I have to ask her. Or you could ask her in the discussion, or you could ignore it and just decide that you don't show up tomorrow. Okay.
Could you ask her to upload an assignment online so that we could?
Why not? Just do it in the discussion. So if you are not showing up, then tell her that she also doesn't come. For example, just let her know. Okay. Thank you very much. Have a good weekend. Thank you, online people. Have a good day. Thank you very much.
Thank you. I have a good day too.
You too. Bye-bye. Yes. The project, yes, please. Just let me stop this.